All right, today we're diving into a machine learning algorithm with a pretty amazing name, Idiot's Bayes. And trust me, as we're about to find out, it's way smarter than it sounds.
So, have you ever stopped to think about how your email knows what's spam? I mean, you open your inbox and poof, all that junk mail about inheriting a fortune or some miracle cure is already sitting in the spam folder. It feels like magic, right? Well, it's not. A lot of the time, the real hero behind the scenes is an algorithm that's built on let's just say, a surprisingly simple, maybe even a little bit naive idea. Some people would call its core assumption totally unrealistic. And honestly, that's what makes this whole thing so cool.
Okay, so let's get right to the heart of it. Why on earth do we call it naive? Well, it all boils down to this one big idea, the naive independence assumption. Okay, so here's the deal. This assumption basically says that every single feature, every piece of information the algorithm looks at, is completely independent of all the others. It's like they have no relationship whatsoever. Now, you and I know that in the real world, that's almost never true, right? That's why the source material calls it highly unrealistic.
And this diagram? It shows it perfectly. See that class at the top? Think of that as our goal, like spam or not spam. The algorithm pretends that the class is the only thing that causes all the features below it. You know, the specific words in the email, who sent it, whatever. But here's the key. It assumes none of those features are connected to each other. They're all just separate little clues pointing back to the main class.
Let me give you a super simple way to think about this. Imagine you're describing an apple. You know that the fact that it's round and the fact that it's a certain size are kind of related, right? But Naive Bayes? Nope. It just sees red, round, and 10 centimeters as three totally separate facts that all happen to point to apple. It's naive. But the crazy part is, it actually works.
All right, theory is great, but let's see this so-called naive idea in action. We're going to walk through a classic example from the source material and build a classifier to predict something just based on a few physical traits.
So, here's the challenge. We've got 3 pieces of data, a person's height, their weight, and their foot size. The question is, can we use just that to guess if they're male or female? Now, common sense tells us these things are connected, right? Taller people generally weigh more. But our little naive classifier, it's going to pretend it doesn't know that. It's going to ignore those connections completely. Okay, first things first, we've got to teach our algorithm. So we feed it this training data you see here. It's got a bunch of examples for male and female, along with those 3 measurements we talked about. This is the raw material, the stuff it's going to learn from.
And this is where it gets really interesting, because the learning part is unbelievably simple. All the classifier does is calculate the average, the mean, for height, weight, and foot size for each group. So it ends up with these 2 super basic profiles, one for what an average male looks like in our data, and one for an average female.
All right, time for the test. We've got a new mystery person. They're 6 feet tall, weigh 130 pounds, and have a foot size of 8. So now the classifier's job is to look at this new person and decide which profile do they fit best, male or female.
So what the algorithm does next is it crunches the numbers and comes up with a probability score for each class. Now, don't worry about the crazy math behind it. All it's really asking is, based on our averages, how likely is it that these measurements belong to a male, and how likely is it they belong to a female? And, wow, you can see right away those scores are not even close.
And the verdict is in. The score for female is just way higher. So the algorithm makes its call. This person is classified as female. That's it. The higher score wins. It really is that simple. Okay, so that's a cool little example. But how do we go from classifying a person based on 3 numbers to tackling the massive, messy problem we started with, sifting through millions of emails to find spam? Believe it or not, the logic is exactly the same. But instead of using features like height and weight, now the features are the words themselves. Every single word in an email becomes its own independent clue, just like red or round were clues for the apple. So here's the breakdown for how this works with spam. The algorithm uses what's called a bag of words approach. That just means it totally ignores grammar and word order and treats an email like, well, a bag full of words. It looks at thousands of known spam emails and thousands of good emails to learn which words show up more in spam. So a word like Viagra or free gets a really high spam score, but a word like your name, that gets a super low spam score. Then for any new email, it just adds up the scores for all the words inside and makes its final call, spam or not spam. And you know what's crazy? This isn't some brand new cutting-edge tech. The source material points out this idea has been around for decades. It first showed up in a research paper way back in 1998,
and today it's a totally standard, battle-tested tool that's humming away inside email clients like Thunderbird and big server-side filters like Spam Assassin that we all rely on.
Which brings us to the final and maybe the most mind-bending part of all this. We have an algorithm that is built on a foundation we know is just plain wrong, the idea that all these features are independent. And yet, it works. It works incredibly well. So what is going on here?
This right here is the naive Bayes paradox. How can something built on a highly unrealistic assumption, something so simple, be so ridiculously effective in our messy, complicated real world?
Well, here's the big takeaway. It turns out its biggest weakness is also its greatest strength. First off, by pretending everything is independent, it doesn't need a ton of training data to get started. But the real secret sauce is this. It doesn't have to get the probability numbers perfect. It just has to pick the winner. All that matters is that the score for spam is higher than the score for not spam. The actual scores could be way off, totally inaccurate, but as long as it gets the final decision right, who cares? It's robust. It can be wrong about all the little details and still be right about the one thing that matters.
And that leaves us with this fantastic question posed in a 2001 research paper that helped make this name famous. Idiots Bayes, not so stupid after all? And I think after everything we've seen, the answer is a definite no. It might be naive, but it's also one of the most elegant, simple, and shockingly powerful tools in the box. Not so stupid at all.